Okay, for X-ray wavelength, lambda equals 22 picometer. The photon energy, 56 kilo eV are scattered from carbon target. The scatter angle is 85 degree. What is the quantum shift? So delta lambda is h over mc 1 minus cosine phi. So we just plug in all the values. 9.11 times 10 to minus 31 times 2.998 times 10 to 8, 1 minus cosine 85 degree. So it is 2.2 picometer. So actually, cosine 85 degrees, pretty small. So originally the quantum h over mec is around 2.4 picometer. This is pretty close to zero. So for part B, what's the percentage of the initial X-ray photon energy is transferred to an electron in such scattering? Okay, one point I forgot to say is the X-ray for wavelength of around 22 picometer, and for visible light is around hundreds of nanometer. So the wavelength is 10,000 times longer for visible light, which means that the energy for X-ray is 10,000 times higher. And what's the percentage of the energy transfer and scattering? So the fraction is originally is HF minus HF prime over HF, and all the H are reduced, and so we have C over lambda prime, C over lambda, and all the C cancels, so it will become lambda prime minus lambda, which is actually delta lambda over lambda prime, which means that delta lambda is 2.2 picometer as we calculate, and originally it is 22. So lambda prime should be 22 plus 2.2 and multiply by 100%. 100%, so it will be 9.1%. 9.1%. So, any questions up till now? So next is about the light. We should regard the light as a probability wave. So we know that light is a EM wave, and light should be regarded as a photon, which is a particle in some case. But is there any relationship between the particle and the wave itself. So now we should regard the light as a probability. Actually, the EM wave still have meaning, even when we regard it as a photon. So the probability that a photon will be detected in any small volume center on given point in light wave is proportional to the square of the amplitude of the E field vector at that point. So first, I need to tell you what is so-called the probability wave. Probability wave. So, you should have learned the probability, but for the discrete case. For example, if we roll a dice, if we roll a fair dice, it would be 1, 2, 3, 4, 5, 6 with equal probability. Equal probability equals to 1/6, right? Or if we flip a fair coin, it could be head or tail with equal probability to be 1/2. So we can actually, in probability sense, we have something called a random variable. Random variable to really mention this stuff. For example, if we just call x is a random variable because if we call x to be the number from a fair dice, which means that h should be a random variable because before you really roll a dice, it could be 1 or 2 or 3 or 4 or 5 or 6. So actually, dice. So this x could be 1, 2, 3, 4, 5, 6, and actually the x should be here we can put 1, 2, 3, 4, 5, 6 here, but if it is like this, we can really write something like x, small x, to be 1/6, or x equals to 1, 2, 3, 4, 5, 6, something like this. So, and this is a probability. P means the probability of this random variable equals to a specific number. And actually, we can write it as this. We can denote it like this. And this is called the probability density function. Probability density function. 几率密度函数. Or in short form, PDF. So this is the simpler case because the result could be continuous. Now, if you imagine you just, for example, we have another random variable called y, but we just draw a real number between 0 and 1, whether it is closed or open, this doesn't really matter. And the probability for each number would be is uniform, something like that. So what is the probability if you pick the number to be 0.5? It should be 0. It should be 0 because there are infinite real number between 0 and 1. So that the probability if you just pick a number to be equals to 0.5 should be 0. However, if you Really need to divide it, it would be something like x, y here, y here. Y would be just 1, 4, 0 between y and 1. And this would be the probability density function. Probability density function is not the same as the probability itself. It means that capital Y will be equals to small y, or should be something like capital Y should be between y and y plus delta y. The probability between here, and if this gap is really small, then we'll say that the probability when we choose a number to be 0.5 is actually 0. It would be more meaningful if I ask you that if I choose a number to be between 0.5 and to be between 0.5 and 0.6, then you say that the probability will be one tenth. But that's how the probability density function works, and according to that, we have even more difficult math behind that. And so, simply speaking, the probability wave is actually a probability density function. And here we talk about the double slit interference, which should be covered in chapter 35.2, but we will not go in it because you might have not learned it in high school. And actually, it means that if we have a plane wave from here, so this vertical line means the wavefront of the light, and it is a plane or a line here, but in the other two directions there should be something. So it is a plane wave. So it is a plane wave, and as long as the plane wave go to these two this board with two slits, then you can regard it as these two slits as two sources of the light, and it will try to propagating to light from these two slits, and these two waves should be circular propagating. If you don't believe, you can go to the lake after the class, and then you throw a stone into the lake, then you find the wave to be circular. Yeah, and actually, after going to the broad, then for some position, the two waves will construct each other, and for some point, the two waves will destruct each other. The constructive and constructive interference and the destructive interference. So at the point here, and so on, this is destructive interference, so that the two waves, which means that the two waves cancel each other, then you feel that the amplitude at that point is very small. Most of it are cancelled, and at this point here, and so on, the two wave superimpose with each other. So you observe many peaks at equally spaced distance. So with this experiment, we know that the light should be wave, but it is something like this experiment should originally be done in in 18 or 19th century. In 19th century, I think in 19th century. So it is quite and actually here we know that the light should be a EM wave, but how can we regard the light is also a photon, which means that the intensity here should be the probability that the photon can go to this point or that point. Which means that if you roll the dice for many times, then if the probability here is higher, you observe more photon at that position. If the probability density is low at that point, then you observe less photon to be at that point. So so we really need to consider light as a probability wave, even for single photon. This is the very strange thing, because when the technology become more and more advanced, the physician can really emit a single photon, and still they can still find even a single photon can interfere with itself. This is the really strange things. So this supports why the photon, why the light should be regarded as a probability wave, because for some time there's some probability to be at this point. For some of the time, it has probability at this point. For another time, it has some probability at that point. So it actually at all the points. But only the probability are different. This is another research which was done in 1992. So it's around. So you have born, I think it is. No, have you born at 1992? I think no. Yeah, 1992 is 27 years ago. 27 years ago. I was born. But you have not born yet for 1992. Actually, so it is not really a long time ago. And for this experiment, main light, and this one I don't know how to call it. This was like a French name, I'm not sure. But it shows that this is a single molecule, and it tries to emit a single photon that take a widely different path. There is one path going from here to a mirror and reflect back, and this is a light splitter. And the other path is this one and go to the mirror to reflect back. So if it has more than one photon, you can simply imagine that the photon can go to here, go back to here, and part of the photon can go to this path, and part of the photon can go to the detector. And if the photon go in the path 2, it can go like this, and maybe go through, and maybe go to the detector. So in this case, if more than one photon was emitted, it really can observe that there is interference at the detector. However, a single photon can take widely different path and still interfere with itself, which means that it only emits only a single photon. And finally, you can observe there are some interference pattern at the detector. So this is very weird, very weird. And so we can see that we can interpret all three versions of double slit experiment. Light is generated in the source as photon. Light is generated as source as photon. And light is absorbed at the detector as photon. And the light travel between source and detect as probability wave. So here is photon, but in between you can regard it as a probability wave. So maybe half of a probability going this way, half of a probability going this way. But actually, even single photon can interfere with itself at the detector. So this is a very interesting research. And actually, I've put a news on the model. And so this one is a recently published research. You can check it here. So this is a news which is easier to read, and this is the original paper. And so it will be more difficult to read. And actually, you can see it like this: a natural biomolecule has been measured at like a quantum wave for the first time. So here, the subtitle is physicians have watched a chain of 15 amino acid 氨基酸一个有15个氨基酸组成的一个抗生素interfere with itself in an experiment that paved the way for a new era of quantum biology. So so it will look like this, and which means that even a 15 amino acid biomolecule also we can also observe the double slit. We can also represent the double slit experiment with such a big molecule, So here we talk about that. As long as here, this is we use the lights for the double slit experiment. But here, the physician after 100 years, they use the electron to reproduce the same result using the photon for the double slit experiment, or for the same experiment. And this is the experiment doing with the arrangement B and X-ray beam. This is using the X-ray, the light, and for C, this one use the electron beam, which is the matter wave. So not only the light has both the particle and wave duality. Here we also know that for the electron is for sure a particle. It also has the wave property, and it can also have some sort of diffraction pattern, 绕射的条纹 diffraction pattern. So we should also we should not only regard the light as wave particle duality, but also for other particle we also should regard it like this. So de Broglie suggests that the E equals h bar omega and P over P equals h bar k should also be applied to the matter, and the wave for the matter should here we call it the matter wave, 物质波. So suggest that P equals X lambda might apply not only to photon but also to electrons. And actually, I just showed you the result, which was published this month. Actually, this month I can show you here. Yeah, here, November 1st, 2019. So this was published this month. So here comes a sample problem. So what is the de Broglie wavelength of an electron with kinetic energy? 120 eV. 120 eV. So okay, the kinetic energy, we usually write it as 1/2 mv squared. But in quantum mechanics, we will usually write it as p squared over 2m. P squared over 2m without consider the relativistic effect, because you can just multiply m on top and on bottom, and mv is actually the classical momentum. So m squared v squared is p squared, so the denominator will have an m. So the kinetic energy is p squared over 2m. And then we can write it as P equals 2mk square root. And it is actually 2 times 9 point electron is 9.11 times 10 to minus 31. Kinetic energy is 120 times 1.6 times 10 to minus 19 square root. So the momentum is 5.91 times 10 to minus 24 kgm over s. So we know the P, and the lambda would be h over P, which is 6.63 times 10 to minus 34 over 5.91 times 10 to minus 24. So the wavelength is about 112 picometer. So this is the de Broglie wavelength of an electron, which is different from the quantum wavelength of the electron. So next, we start to enter the quantum mechanics. But the first weird concept is the wave function. Psi is the wave function, can be used to describe the matter wave. Because we know that a matter should be described by a wave called the matter wave. And phi is the notation for the matter wave, and then its space and time variable can be grouped separately and can be written in the form like this. So phi should be a function of x, y, z, and t, something similar to the EM wave. When we solve the wave equation in chapter 34. So the E field should be something look like this, but here it is psi, capital psi, but not E or B. And for some case, if it is not really, if it is say stationary, we can separate the time function with the space so that we can write it like this. We can write it like this. And here, omega is the angular frequency. And suppose that a matter wave reach a particle detector, the probability that the particle will be detected in time interval is proportional to the square, absolute square, which means that the probability. So the probability that the particle is at xyz is the probability that the particle is at xyz at a given time. At a given time is actually we take this absolute value and square. You may ask, why do we need the absolute value? Because this function is a complex function. This is a complex function. This is not a real function. This is complex function, which means that, for example, if you imagine 1 plus j2, j is square root of 1. If you just square it, it will become 1 minus 4 plus j4 equals minus 3 plus j4. So actually, if we really need to find the absolute value of it and take the square, which is actually you calculate itself multiplied by its complex conjugate. Then it will become 1 plus j2, 1 minus j2. Then it will become 1 plus 4 equals 5. So for the absolute value of this, you can make it like square root of 5 exponential to j arctangent 2, something like this, arctangent 2. So this is the polar form of this complex number. Then if you really find the absolute value and take the square, it will something like this, because it does not really relate to the angle of this complex number or complex function. So actually, we really need to calculate the phi, the absolute square of the wave function, and this is the the only physical meaning for the wave function. No. There's no physical meaning for the wave function itself. This is very strange. Because when you solve the wave equation, the solution itself is the E field and the magnetic field, and actually you can really measure it. You can really observe the E field is something like a sine wave or something like that. But here, there is no any physical variable that can be shoot to this wave function. Only the the absolute square is the probability of the particle, and this is called the Copenhagen interpretation. If you can find on the internet, this is called the Copenhagen interpretation, which means that this one is the probability that, or the probability density function, that a particle is at a certain position. So here it summarizes the probability per unit time of detecting a particle in a small volume center on a given point in a matter wave is proportional to the value of the absolute square of psi at that point, because psi is also a function of xyz. So you plug in xyz, then you can know the probability density function that the particle is at that point or at a interval. Then you can just integrate over that volume. So here just tell you this is actually the Schrödinger equation, and in the next lecture I will tell you how we can derive it, because it is not really come from derive. We really need some postulate to make this equation make sense, but you cannot fully explain it. Why we need to make this postulate. And actually you can make these two postulates to derive all the equation, and you can make other two postulate or some postulates, then you can derive the whole group. But actually you cannot really distinguish which should be the source. But all of them are compatible. But the point is, if you can make less and less postulate, then it will be better. Because if you make a postulate, which means that the postulate can be wrong. You don't know why it is wrong, but as long as you find an experiment to show that this postulate is wrong, then it means that the whole theory deriving from this postulate is all wrong. But for the next lecture, I will try to explain how this equation comes from. And if we consider h equals h bar equals h over 2 pi in here, then the equation will look a bit easier, because this term is only 2m over h bar squared. Here it is something like 8 pi square m over h squared. So this not a little bit nicer. So here phi is of course the wave function, and we take the second derivative with respect to the space, and here E is the energy, is the kinetic energy of the particle, and U of x is the potential energy in the space, and the mass is also m is also the mass of the particle itself. So if we can really solve this Schrödinger equation, then we will know the wave function, which can tell you some information about the particle. So here, if we just let the U of x to be 0, and E is the kinetic energy, if we substitute E to be 1/2 mv square, so that it will become this is mv square, so that it is p square, and 2 and 8 are reduced to be 4, so we have 4 pi square, so that this is 2 pi square, and h, so we can group it like this. This is 2 pi p over h, and p over h is lambda according to the de Broglie wavelength is 1 over lambda, 1 over lambda. So that 2 pi over lambda is the wave number k, and the Schrödinger equation will become like this. This is a second order differential equation. So if we just solve this second order ODE, the solution should look like this. Which means that if you just plug in phi equals to exponential to s x, then this will become s squared exponential to that term plus k squared equals to 0, and exponential to sx is reduced because it is not 0. So you will know that s is plus or minus jk, or ik here. So the solution will be a times exponential to ikx plus b times exponential to minus ikx, similar to what we derived in for the wave equation. And here a, b are complex number, complex constant. So here, so consider particle that travel only in positive direction, which means we only consider this term. We just ignore this term first because it is linear, so that we can consider one term first, and then fine, you can add them together if you like, or if satisfy the initial condition or boundary condition. So if you only consider the wave that propagate in the positive direction, so the phi x will look like this, and we label a to be phi 0 here, so that we want to know the probability of the position of the particle. Actually, this case is only one dimension. So we just take the absolute square for phi x, and we substitute the answer to here. And phi 0, here we just assume it is a real number, or maybe imaginary, or maybe complex is not a big problem. We only need to add a absolute value here. So when two numbers multiply together and we need to take the absolute value, we can just separate it something like this, eikx, and take the square, and the square will go to the first term and the second term, so that we'll have a phi 0 square and this term square. So what is this term? This is actually 1. Because according to the Euler's equation, Euler's equation EI kx is cosine kx plus I sine kx. So if you just find the absolute square, which is not only which is nothing but cosine square kx plus sine square kx, and which is of course 1. So finally, we will find that the probability is actually a constant, which really makes sense because in this case, we don't really have any potential, which means that this particle is free. It is free, which means that it can be anywhere in the space. You don't really know where it is. The probability that the particle at this point or at that point or at that point is actually the same. You don't have any information about that. This is what it tells you. A free particle should look like this. Should look like this. You cannot know where it really is.